Okay, so let's do some math in analyzing this model. We could actually figure out the final size of the epidemic by doing some algebra manipulation and integration by separation of variables. We could do that because we could actually eliminate one of the unknowns from the first two equations. So notice if we factor I, we could divide the second equation to the first, and I prime, think of I prime as di dt, because that's what it is, the derivative with respect to t, and divided by s prime, which is ds dt. We get lambda s minus r minus di over minus lambda s I. So notice I cancels, and we could think of I as a function of s or vice versa. So we could eliminate the time and essentially end up with an ODE in terms of I and s. And we can integrate basically this ODE and find a relationship between I of t and s of t. By the way, that doesn't happen most of the time in more complicated models, but it does in this case because of our lucky situation that I cancels when we divide those two equations. So let's clean up a little bit the equation here so we can distribute the lambda s. So we have lambda s over minus lambda s, and then plus r plus d over lambda 1 over s, which is minus 1 r plus d over lambda 1 over s. I want you to keep in mind this because when I'm going to run the example, I'm going to play with these values a little bit to make the case that we talked about with whether it makes a difference if you reduce the probability of transmission just a little bit. So at this point, again, if you didn't learn separation of variables in the ordinary differential equation class, it might be a little bit strange, but it's still just calculus. Think of this as the equality of two differentials. So I'm going to multiply both sides by ds. So on the left side, think of a function in I only, which is just 1 times di, a differential in I. And on the other side, a differential in s. And now we're going to integrate both sides. So the integral of 1 di in terms of I obviously is going to be I. Here in terms of s, we get minus s plus r plus d over lambda, the integral of 1 over s, which is ln of s. By the way, one can prove that the solutions are always positive if you start with positive values. There's a little bit of math behind that, so for now we just assume that, of course, these properties are satisfied on this equation. And don't forget the concept of integration, as with all antiderivatives. Now, the concept of integration comes from initial conditions. So remember, IS stands for I of t, S of t. So if you replace t with 0, you're going to end up with the initial values of the population. So let's say S naught, I'm going to later on maybe replace S naught with 999, as I mentioned before. But S naught, is the initial susceptible class, I naught the initially infected class. So when I plug in 0 for t, this entire equation will give me a way to compute that value of the integration constant. And so the integration constant is I naught plus S naught minus r plus d over lambda, natural log of S naught. Put it back in the equation between S and I, and let me move minus S to the left. So we have r plus d over lambda, natural log of S, plus the constant of integration that we just found. And we're going to do a little bit of more simplification here just to make it more compact. I can combine these two terms, pull out r plus d over lambda, and then the difference of ln of s minus ln of s naught, we can write it in a more compact form, ln of s over s naught. And then I naught plus s naught, again, are the summation between the initial infected and the susceptible class. So in fact, let's actually use, as I said before, that case when we have the start of the epidemic when I naught is 1, S naught is 999. So just one infectious person, one infected person in a population of 1,000 people. Furthermore, one thing I want to mention before we move on. Remember that eventually we established that I of t goes to 0. So that's the key thing that we have to understand before we move on to the example with, I'm going to actually do it in Wolfram Alpha, not with Maple, but the example that computes the final size of the epidemic. So this relation gives us the relationship between S of t and I of t at any time t. Okay, so no matter the time t, S of t, I of t always satisfy this equation. Eventually, if I of t goes to 0, if I replace I with 0, what's left is an equation that will give me the final size of S. Because I know that I is 0 only at the end of the epidemic. So when I replace I of t with 0, let's write it on a second piece of paper. We have the equation for the final size of S of t. So I is 0, which means there's only S on the left-hand side, R plus D over lambda, ln of S over, and I said that I'm going to use an initial susceptible population of 999 people, plus I naught plus S naught, 1,000 people, total population. So this is the equation I'm going to play with in Wolfram Alpha in the third part of the video. Again, let's review briefly. We could integrate the model. We could find a relationship between susceptible and infected at all time t by replacing I of t with 0. Whatever I get for S will be the final size of S. So remember, what we're looking for, the good news will be the bigger the better. So the bigger S final, the better, because it means that eventually not so many people were infected. And in my example, like I said, I chose R to be 0.07. I chose D to be 0.002. And then I'm going to play with lambda, and I'm going to illustrate those terms that I talked about, that they come up from essentially 3 products, right? I mean, the fraction of the people met in a given day. So I'm going to use, for example, in the first example, let's say the person on an average day meets 10 people. So there will be 10 times over 1,000, or 0.001. And then the probability of meaningful contact. Okay, so how likely that infected person is to come close enough for the transmission to occur. And then we're going to say maybe that's 1 over 10. And then how likely is that person to shed the virus, basically, okay, to transmit the virus, okay? And then we can take basically another probability. Again, I'm making up numbers here. We can assume that they are either low or high, but my point is to show the impact if we basically nudge one of these lower or higher, right? So for example, you know, if the person wears the mask, one can assume that the probability of shedding the virus is going to be much lower. But if we think it from the point of view of actually whether the person healthy gets the disease, we can nudge the probability even by a small amount, and we will see the difference in the size of S by running these equations. So in my last example, I'm going to do just that, and we're going to just see what happens if one of these probabilities is just a little bit modified. Okay, not dramatically, but just a little bit. And then we can play also with the number of people met in a given day to see if the quarantine measures, for example, how effective they are, right? I mean, if the person quarantines himself or herself, that means the average number of people that the infectious person meets in a given day, then it's lower, and so on. So with that being said, we're going to run this equation with Wolfram alpha and discuss further the interpretation of the results.